Hello students, we are going to discuss about a practical differentiator circuit. The target which we have defined is a design, build and test practical differentiator for a frequency FA is equal to 800 Hz. We are going to use IC741. The pin configuration is pin number 2 is inverting pin number 3 is a non-inverting terminal, pin number 6 is output pin number 7 is plus VCC and pin number 4 is minus VEE. We are designed a practical differentiator circuit in which we are connecting this resistive element in series with a capacitor, and in this circuit we have connected one capacitive element in parallel with resistive element. Here we have connected offset minimizing resistor in the circuit, and that's why this is a practical differentiator circuit. The problem with the ideal differentiator circuit, that is high frequency noise elimination, can be obtained by using this capacitive element connected in a feedback path. The design equation is FA is equal to 1 upon 2 pi R1C1. The design which we have considered is FA is equal to 800 Hz. The equation is FB is equal to 20 times of FA. So FB is equal to 16 kilohertz. FB is equal to 1 upon 2 pi RFCF. With this consideration, let C1 is equal to 0.1 microfarad, CF is equal to 4.7 nanofarad, and by putting these values of C1 and CF in these formulas, we have RF is equal to 2.2 kilo ohm, R1 is equal to 100 ohm, and ROM offset minimizing resistor, which is a parallel combination of RF and R1, which is approximately equal to 100 ohm. So we have designed this circuitry for FA is equal to 800 Hz. FA is a frequency in a differentiator at which the magnitude plot has a value 0 dB. After that, as frequency increases, the output goes on increasing, and at F is equal to FB, the output start decreasing, means gain start decreasing after this F is equal to FB. So the equation for a differentiator is V0 is equal to minus RFC1 into d by dt of V. This is the basic circuitry of differentiator. The readings which we are going to take over here are, we are going to apply 1 volt peak to peak sine wave input signal. We are going to increase the frequency from 100 Hz and we are going to measure the output voltage for each frequency. This is the calculation which we are going to obtain, that is gain is equal to output voltage upon input voltage. Input we have considered 1 volt peak to peak signal. Then next column is gain in decibel, that is 20 log of V0 upon Vin, and finally we are going to plot the graph of gain in dB versus frequency, that is gain we are going to plot on y-axis and frequency on x-axis, and that we are going to plot on a semi-log paper. The response of differentiator we are getting like this. This is the gain in dB and this is the relative frequency. This is the open loop response of a operational amplifier, and this is the response which we are getting for a closed loop response for a basic differentiator circuit, that is 20 dB per decade. This is a frequency FA at which the magnitude is 0 dB and this slope is 20 dB per decade. At F is equal to FB, when we have connected a capacitive element in a feedback path for a practical differentiator circuit, after this frequency gain starts decreasing. So this is FA and FB. Theoretically this is 800 Hz and FB is equal to 16 kilohertz. Now we are going to check the practical results for this circuit. Normally for differentiator, if we are going to apply square wave signal, we are getting spike at the output side. Let us see how we are going to perform the experiment. This basic instrument which we are going to use is a function generator. For the function generator, we have by using function generator we applied 1 volt peak to peak sine wave input signal, which we can see on this DSO. If you see, if I will vary the input magnitude, the output is also changing. We have connected input signal to channel 2, output we have connected to channel 1. Now we are going to take the measurement one by one. Let us start. This is the instrument. By using this knob we are going to vary the frequency. By using these two knobs we are going to select the range. By using these two knobs we can attenuate the input signal, means we want to apply 1 volt peak to peak input signal. For these two knobs we are going to use, and by using this terminal we have connected the input signal to our circuitry. Here you are getting the display of function is a sinusoidal, and this is the frequency which we are going to apply. The another instrument which we are going to connect here, is a multiple power supply. We are going to apply a dual power supply to our op-amp. We have connected plus VCC to pin number 7, minus VEE to pin number 4, and common we have connected at the ground side. The output we are going to observe on a digital storage oscilloscope. If I am going to set the input frequency to 100 Hz now, we will take the first measurement. We are adjusting the frequency to 100 Hz. Now see the results. The output which you are going to observe is yellow in color, which is initially at a very low value, that is at 240 millivolts. Now at 100 Hz we are getting approximately 200 millivolts, and as we go on increasing the frequency, if we will take the second measurement at suppose 500 Hz, we will adjust the frequency to 500 Hz. If you will see, the output voltage is now moving towards 1 volt. At 500 Hz we are getting around 824 millivolts. If we take the reading at 500 Hz, the output voltage we are getting around 800 to 900 millivolts. If we will take the frequency to now, we are getting the output voltage is equal to approximately 1 volt, which is at around 750 Hz we are getting. So which indicates that the design frequency FA we have selected 800 Hz, and practically we are getting around 730 Hz to 750 Hz. If we still go on increasing the frequency, the output voltage continuously goes on increasing. At around 2 kHz, we are getting the output voltage is increasing, and it is 3.08 volts. We go on increasing the frequency now. The next reading we will take at 5 kHz. At 5 kHz, if we will observe the measurement, the output voltage is 6.68 volts. If we still go on increasing, at 8 kHz we are getting 8.88 volts. The output is still goes on increasing. At around 12 kHz we are getting the maximum value, and after that the output start decreasing. So the design for differentiator FB we have selected as a 16 kHz, and practically at 12 kHz we are getting the output voltage is 9.52, which is decreasing. Means FB we are getting 12 kHz. After that, if you will observe the measurement, still the output voltage now goes on decreasing. Means whatever the graph which we have considered, initially the output voltage increases and then the output voltage decreases. That also obtained over here. Another important thing is, as if you see the waveforms, in the waveforms, if you will see, there is a 90-degree phase shift existing between the input waveform and the output waveform. That is, for sine wave input signal we are getting cosine as the output, and the output is a minus of RFC 1 into d by dt of Vn, so we are getting negative value. and that's why we have obtained the differentiation of input signal, that is sine wave signal is converted into cosine wave, and the equation which we have discussed here is obtained. If we focus on the circuitry, here we have connected 100 ohm resistor. This is a 0.1 microfarad capacitor, and the input signal is applied to this series combination of RC. This resistor of 100 ohm we are connected between pin number 3 and ground. Between pin number 2 and 6, this is a parallel combination of 4.7 nanofarad and 2.2 kilo ohm resistor we have connected. Hence, the differentiation of input signal is obtained at the output side, and whatever the theoretical discussion we have done, that is obtained practically also. Thank you.